So as for your control work, it is almost checked. So the results will appear soon. This is the first thing. The second thing, I will discuss a couple of problems, but I will just write down the solutions. So I don't want to spend the time of the lectures for this. The third thing, that we'll have the second control work in 2 weeks. So this will be the last lecture. So this will be 16th of December. And now let us, in the same manner, I will ask you to choose several exercises before this control work to discuss, and I'll write down the solutions as it was the previous time. So now let us pass to the lectures. So today I will discuss some applications of Markov chains, and I will start with the very beginning with some funny non-serious applications which were made by Markov, and then I will finish by serious applications, serious modern applications, namely by decoding encoded texts using Markov chains. So the very first application it was made by Markov in 1913. So Markov suggests the following thing. He took the novel by Pushkin, the Evgeny Onegin, and he analyzed 20,000 letters, 20,000 subsequent letters of this novel. So in fact, he suggested the following, what he wanted to do. He suggested to look at the text as to a realization of certain random process. And so the states of this random process are letters of Russian alphabet. So what is the simplest possible model for the text as for the random process? The simplest possible model is when you assume that all letters in the text are just independent random variables. Independent random variables. So this is an alphabet, and these random variables, they belong to the alphabet. So how to find the distribution of these random variables? You should do this just statistically, and that's what Markov has done. So he analyzed 20,000 letters of Evgeny Onegin, and then he was interested in frequency of vowels, частоту гласных, and of consonants. То есть частоту согласных. So this is empiric frequencies. He found some numbers. And then he assumed that vowels and consonants. So in fact, no. He didn't consider the state of his random process. He didn't consider the whole alphabet as the state of his random process. He considered only 2 states, vowels and consonants. So, то есть его случайные величины, значит, могли принимать 2 значения, либо гласное, либо согласное. And he found empirically the frequency of vowels and consonants. And then he tried to understand if this model is satisfactory or not. How can you do this? He just compared the variances. So you get your random variable psi, which takes two which takes two values, vowel and consonant, and then he computed the, okay, you can say that if it's vowel, then it's 0, if it's consonant, then it's 1, and he computed the variance of this random variable according to the model that all random variables are independent. So if you have independent, identically distributed random variables xi, right? So xi1, xi2, xi3, xi4, this is your text. Sorry, so I think that I explained not very properly. Let me try to explain again. So what we are doing, we are trying to model the text as a sequence of independent, identically distributed random variables, right? These random variables. So now, for the moment, we are interested only in if the letter is vowel or it is consonant. Значит, гласная или согласная. And we assume that these random variables are independent, identically distributed, and just empirically we find the frequency of vowels and consonants. What is the frequency? We consider them as a probability. So if the frequency of vowels is p vowel and the frequency and consonants is p consonant, we find these frequencies empirically, then I assume that these random variables have distribution, the probability that xi j equals to so 0 is vowel, right? Equals to p vowel, and probability that xi j equals to 1, this is p consonant. And then according to this model, I can compute the variance of xi j. So of course we know how it behaves. It behaves as p consonant times p vowel, right? So this is simple computation. And then you can compare this variance with empirical frequency, empirical variance, which you can find just analyzing the text. Compare with empirical frequency. And then, actually, this is not surprising. Markov found that it is in bad accordance. In bad accordance with the empirical frequency. So, is it clear what I'm explaining or not?
Sorry, we should compare our theoretical variance with empirical variance, but not empirical frequency.
Thank you, Camille. With empirical variance. And then he concluded that this model is not satisfactory. Actually, it is not surprising, because if you just take letters of the text at random, then it will not resemble the text, right? Then Markov suggests different model. He suggests to the following idea. Let us model the text as a Markov chain. So now we do not assume that all letters in the text are independent, but we assume that the next letter depends only on the previous letter, right? Of course, this is not true for real text, right? But let us consider this model. Maybe it will give something. Then he found, just analyzing Eugene Onegin, he found these 20,000 letters. He found the empirical transition probabilities. So now the Markov chain, it has two states, vowel and consonant, and you have transition probabilities, p vowel from vowel to consonant, p from consonant to vowel, p from consonant to consonant, and p from vowel to vowel. He found actually that p vowel equals 0, 1, 2, 8, p consonant vowel equals, so these are empirical probabilities, right? P vowel consonant equals accordingly 1 minus p vowel, and p consonant equals 1 minus P consonant vowel, right? So then he also found yes, this Markov chain is mixing. So sorry, it is ergodic. It is ergodic. So it has a unique stationary state. He also found the stationary distribution, and the stationary distribution, so it has two components, P consonant and P vowel. So first I write vowel, right? So we should write like this. P vowel, P consonant, and he found that P vowel, this is 1, 0, 4, 3, 2, and P consonant, this is 0, 5, 6, 8. 5, 6, 8, right? Okay. And then you can compare the frequency of vowels and of consonants. Sorry, not the frequency, the variance. So now your Markov chain is Xi0, Xi1, Xi2, etc. And you can find variance Xij, say for large J, and then he found that it is in rather good accordance with the empirical variance. So at least the accordance was much better than in the previous model, when you assume that all letters are independent, identically distributed. Okay, so this was just a funny exercise. Then Markov, he wasn't lazy at all, because then he analyzed 1,100 letters of Aksakov's novel, The Childhood of Bagrov. And he found very different transition probabilities and very different stationary states. For example, he found that the transition probabilities from vowel to vowel equals for Aksakov to 0.552. Okay, and for Pushkin it was 0.138. You see, the difference is very serious. And then so for him this was a funny exercise. And then but some philologists, they have taken this for serious. For example, philologist Morozov, he was very enthusiastic about this approach, and he told that this can be viewed as a new weapon for analyzing ancient scripts. So, for example, you find ancient script, and then you wish to understand who is the author, and you have, for example, you have like 3 candidates for the authorship of this text. Then you consider this text as a Markov chain. You find the transition probabilities, and if the transition probability is close to the transition probability of which is usual for one of these authors, then you can suggest that the authorship of the text, right? Значит, если вы находите переходные вероятности в вашей модели вот в этом самом тексте, чье авторство неизвестно, близкими к переходным вероятностям какого-то автора, то есть характерным для какого-то автора, ну тогда можно подумать, что, может быть, текст принадлежит тому же автору. Okay, but actually this method wasn't used, and Markov didn't take this really for serious. Let me just show the copy of the page of this Markov's work. So they weren't lazy at all, these guys at that time. You see, he really analyzed in total 120,000 letters. So it was like this. You see, this is indeed Евгений Онегин, мой дядя самых честных правил, когда не в шутку за ним мог. And here he computes the number of letters, he computes the number of vowels, the number of consonants, and so on and so forth. You see, so this was nice. Okay, so this was like the very first application. Now Markov chains are widely used. These are one of the most of the most used models in physics, in biology, in financial mathematics, and so on. Or usually these are not just Markov chains and discrete Markov chains. Usually these are some continuous time Markov processes, but the basic ideas are already here. So the implementation is more complicated by the basic ideas. The Markov property is already here, as in the Markov chains. So it would be natural that the next application, the next real-world application, would be found in these areas, like in physics or in biology. But surprisingly, the next, like the first real-world application was similar to what Markov suggests in this his funny work about the Pushkin and the Aksakov texts. The next application was suggested by Claude Shannon. And this application to the information theory. I will not talk about this in details. I will just say a couple of words. Actually, Shannon invented codes which correct errors. Codes which correct errors. Just wait a second, please. Okay, so as far as I know, the story was, yeah, and this is 1948. As far as I know, the story was as follows. Shannon was at that time a young researcher, something like assistant in information theory, and so at the time computer, this was very extremely large machine of the size of like a room in the school where you do sportzal, and the computers were very slow and very bad and very large and very expensive also. So if you work in information theory, you need sometimes to use computer nevertheless, and people, they had a certain amount of time that they were certain slots, certain amount of time that they were allowed to work on computer. And if you are assistant, then this amount of time is very small. And then when computer starts to work, you pass some data to computer, and sometimes computer lost some packages of data you give him, and then everything stops. And you should restart. But you do not have this happens sometimes. But if you do not have a lot of time, a lot of computer time, a lot of machine time, then I mean you have problems because you gave these packages, then one of the packages is lost, and then your time is finished. So you do not have time to restart. You will retry. You will restart only in a week when you have the next slot of machine time. So, and Shannon was in this situation, and then he started to think how to avoid this problem, and finally he invented codes which correct errors. So roughly speaking, what are they doing? They're trying to predict what was in the lost package of data. Namely, okay, for example, if you pass a certain word to computer and one letter is lost, so you should try to recover this letter. And to this end, Shannon used exactly this idea of Markov. So he modeled the text as a Markov chain, and then he predicted probabilities. Of the letters, and then you can predict which letter was lost actually. So, and this is very, very, very famous things, this error correcting codes by Shannon. So now let me pass to the next application. This is possibly the most known application. This is a PageRank by Google. So what search in Google does? So Google does two things. When you ask Google something, first, Google needs to find all pages which are related to your question. And second, possibly the most important thing, Google needs to sort these pages in such a way that the most important pages are in the beginning of the list of the list of pages he will show, right? So, and this algorithm which sorts pages, it's called PageRank. So maybe now PageRank doesn't work anymore. I am not sure, but at least several years ago it was still working. Of course, it was modified like thousands of times, and it became much more complicated than I will describe. But what I'm describing, this is like the simplest version of the PageRank, the very first version from which everything was started. So the idea is, let us think about the internet as about a Markov chains. The states of this Markov chains are web pages, and between web pages you have links, right? And then actually Google has not very high opinion about users, because he assumes that the users does the following. The users do the following, that they arrive at some web page, for example, this one, and then they look at links which or at outgoing links from this web page. For example, here there are 3 links, and then Google assumes that user chooses a link by which he passes at random, and then the process is continued. Namely, namely the idea is the following. Let us consider the Markov chain with the following transition probabilities. If L, this is a number of pages, of web pages in the internet, then I consider the Markov chain on the state space 1L, and for every I from 1L, I define the number L of I, which is just the number of outgoing links from the page I. So here you have the page I, and for example, it can be you can have links to page J, R, and K, and then for this picture, L of I equals to 3. And then let us consider a Markov chain with the following transition probabilities. Pij equals to, so let me for the moment put P hat, okay? Because then I will change these transition probabilities, equals to 1 over L of I, if L of I is not 0. So if you have some links which go from this page to another page, if L of I is 0, so if for the web page I you do not have outgoing links, then you just type random address in the browser and go with equal probability to arbitrary web page. And otherwise, sorry. If so, Pij equals 1 over L of I if L of I is not 0 and you have link from I to J. Okay, so by this I mean that you have link from the web page I to the web page J, and 0 otherwise. So if you have a link from the web page I to the web page J, then you go to the web page J with a probability equal to 1 over the number of links outgoing from the page I. If you do not have links, you have 0 links from the web page I, then you type random address in the browser. And if you have links from the web page I, but there is no link which leads to the web page J, then the probability to go from I to J is 0. Okay. And now, so now let's consider this Markov chain. This Markov chain is not very good, actually. Why? Why it is not very good? Just because we like Markov chains which are ergodic, and this Markov chain it can be not ergodic. This Markov chain can be not ergodic. How is it possible? Can you suggest some picture for this? Situation. No ideas. So look, it is actually this very simple situation. When
probably we can have an isolated vertex.
Yeah, so or just for example, your internet is separated into 2 parts which are not connected, right?
Yes. Then
here you have links only to this part, and here you have links only inside of this part. And then your Markov chain will not be ergodic, because if you start from the distribution here, then you will stay here, and if you start from any distribution here, you will stay always here. That's why it means that it's impossible that you have convergence to the unique stationary state, right? So to avoid such problem, let us modify slightly this Markov chain, and namely consider a Markov chain with the following transition probabilities. They're equal to the transition probabilities Pij, but multiplied by some factor 1 minus alpha, and plus alpha over L. And initially, in the initial implementation of the page rank, as far as I know, alpha was equal to something like 0.15. So what does it mean? It means that with probability 1 minus alpha, the interpretation is as follows. With probability 1 minus alpha, user choose at random any outgoing link from the web page and clicks this link, okay, and arrives to a new web page. But with probability alpha, which is quite small, he just types a random address at the web at the browser, and he goes to arbitrary web page. Okay, so now all Pij, they are strictly bounded from they're away from 0. They're more than or equal to alpha over L, and that's why transition probability matrix is mixing, and this means that the Markov chain is ergodic. And if it is ergodic, it has a unique stationary state, right? And what PageRank suggests is to sort the web pages according to the stationary distribution. So PageRank, if Pi is more than Pj, then the web page I goes first. Значит, если стационарная вероятность странички I выше, чем стационарная вероятность странички J, тогда страничка I появляется в выдаче раньше, чем страничка J. Okay, so actually the creators of Google, they published paper suggesting this algorithm, and in the next year they created Google. So this played like a fundamental role. And why this gives a good result? Just because if we assume that the behavior of users, okay, why it gives a good result? Because if some web page has high stationary probability, roughly speaking, it means that there are a lot of links which go to this web page, right? It means that this web page it should be important, right? For example, there are a lot of web pages which have links to Wikipedia, right? And that's why Wikipedia is important, and that's why Wikipedia in the top of the sorting. But the problem is how to compute this stationary distribution. The first idea is just to find the left eigenvector of the transition probability matrix corresponding to the eigenvalue 1. But from the computational point of view, it is too complicated problem. So it doesn't work good because the size of this matrix, of this transition probability matrix, this is L times L. So this is huge, and the problem of finding of its left eigenvector is computationally very complicated problem. That's why another approach is used. So you just start from arbitrary initial distribution pi 0. In fact, it would be better try to choose this initial distribution in quite a reasonable way, not very special way. For example, something which you expect to be close to the stationary distribution. But roughly speaking, you start with arbitrary pi 0. Then you know that Pn will converge exponentially to the stationary state P, to the stationary state pi due to ergodic theorem. Due to the ergodic theorem, right? And this convergence is exponential. This is very fast convergence. And computing Pn, this is much simpler problem than problem of finding eigenvalues, eigenvectors of the transition probability matrix pi. So you just need to make a number of so you should compute this Pn for n which is not too large, and then this Pn will be stabilized. So it means that it is almost, I mean, it means that it is already close to its limit, which is the stationary distribution. In such a way, you approximately compute the stationary distribution pi. You see? Of course, there are a lot of problems here. For example, there is a problem that you can have like a quasi-stationary states. It means that this sequence is stabilized for a certain time, but then it continues to evaluate. And this first stabilization, this was not the true stationary state. This was some another state which is like almost stationary, but is not stationary, and it can be very different from the true stationary state. So there are some problems, but and you can create an algorithm which really works using this idea. Of course, there is another problem. You need to efficiently find efficient way to compute these distributions Pn. So you need to multiply efficiently vectors of very large dimension to the matrix of very large dimension. So some advanced linear algebra algorithms are included here, but it works. So for me, this is a very nice application. Why? Because just usually in real world applications, people use not theorems from mathematics, but people use objects. For example, when you analyze like flows of petrol or something like that, трубопроводы, then you just write down a system of differential equations and you solve the system of differential equations numerically. The same is when you do your meteor forecast, right? You write down a system of differential equations and then you solve the system numerically. So here you use object, you use differential equation. But here in this application, in this PageRank algorithm, you use theorem, you use the central theorem of the theory, you use the ergodic theorem. You see? So this is very nice from my opinion. Okay, so these were somehow simple applications. Наиболее хайповые я вам рассказал, это значит PageRank. And now let us pass to some more complicated applications. Do you have any questions till this moment? No questions. So then let us start with the Metropolis Hastings algorithm. So this algorithm I will give you as an abstract problem, but then I will use it in the next application I'm going to discuss. This will be the decoding of texts. And I will start with the exercise. This will be your homework. Exercise. So assume that we have a Markov chain with the transition probabilities satisfying the following relation. Pi I Pij. Transition probabilities here, as usual, are Pij, and of course the Markov chain is homogeneous. Equals to pi j Pji, and this should be held for any I and j. And moreover, here pi, this is just a certain distribution, given distribution. So you fix distribution pi, and then it turns out that this relation holds for arbitrary I and j. Then I ask you to show that pi, in fact, is a stationary distribution. Stationary distribution of the Markov chain. Another question, if this assumption is necessary or not. So this is a sufficient assumption for pi to be a stationary distribution. This I ask you to show. But if this assumption is necessary, so this I will leave you also as an exercise for your homework.
Sorry,
Now,
in this question, do we have a finite Markov chain or no?
this is not important. This is not
Okay.
important. It's not important. So actually, when do I need the Markov chain to be finite? Usually I need it in some theorems like ergodic theorem, right? And here this is just simple computation, in fact. So here you do not need the Markov chain to be finite. Okay. What I want to say? Well, now let us assume, let us consider the following situation. So we are given, so we have again a Markov chain with transition probabilities Pij. Again, it is homogeneous, right? And we have certain state pi, just as before. In general, pi is not a stationary state. So now I do not assume this equality anymore. Now just I restart from the beginning. I have a Markov chain with certain transition probabilities, and I have certain distribution. In general, I do not assume that this distribution is stationary. But what I want to do, I want to modify my Markov chain, that is to modify the transition probabilities in such a way that this state pi becomes a stationary state of the modified Markov chain. Of my Markov chain with these new transition probabilities, with these modified transition probabilities. So how one can do this? Just in the following way, I suggest you to modify. Also, this is the assumption which I make for simplicity. This is not necessary. If it is not satisfied, then I mean, just working more, you can do more or less the same. So I assume that if the transition probability from a state I to a state J is non-zero, then you can go to the other direction with non-zero probability as well. Okay, so this is an additional assumption. Well, so I will try to modify my Markov chain. So I will try to use the exercise. Since I will refer to this exercise, this will be exercise 30. Because the previous lemma was 29. So I will just try to modify my transition probabilities in such a way that this equality holds. How I will do this? I will denote new transition probabilities by Qij, and I will choose them in the following form: alpha ij pij, if I is different from j, and if I is equal to j, I choose the transition probability in such a way that sum of all outgoing transition probabilities is 1, as it should be for Markov chains. That is, this transition probability equals to 1 minus sum over all j, which are different from I, alpha ij, pij. Okay. So then the sum over all j of qij is 1. And now I wish to choose alpha ij in such a way that pi is a transition probabilities. So according to the exercise 30, it suffices to choose alpha in such a way that this equality holds, where replace pij and pji by qij. That is pi I qij equals to pi j qji. Look, qji. Of course, here it suffices to consider the case when I is different from j, because if I is equal to j, then this holds automatically. Then it means that pi I divided over pi j equals to qji divided over qij. That is qji, q's are given by this formula. So alpha ji pji over alpha ij p. Sorry. I want to find alphas, right? I want to find alphas. That's why let me put it in a different way. Since I want to find alphas, then I write the following. This equality is equivalent to the following: alpha ij over alpha ji should be equal to what? Pj pi j pji over pi I pij. Okay. Also, we can have problems if pi equals to 0. That's why I make an additional assumption that I forgot to make. Pj is different from 0 for any j. For any j. Yeah, actually. Well, okay. Well, and now I can choose arbitrary alpha such that this is satisfied. Of course, I need the probability to be bounded by 1. That's why, in particular, I need that alpha ij, they are all bounded by 1. Right? And now I wish to choose them maximal. Later you will see why. I wish to choose alpha ij maximal possible. So how then I can choose them? Do you understand or not? Possible, but alpha ij is bounded by 1. Yeah, of course, there also should be non-negative. Okay, so I should take alpha ij to be equal to minimum between 1 and pj pi ji over pi pi ij. Look, why? Because what does it mean? If so look, I wish to maximize alpha ij, right? Since they should be bounded by 1, it means that what do I need to, which properties should be preserved? First, that alpha ij is bounded by 1, and second, that this relation holds. It means that the maximal between alpha ij and alpha ji I should choose as 1, right? And minimal of them I should choose in such a way that this relation holds. This is exactly written here. Just a second. I plug my laptop. Okay. Is it clear?
Not really. So we want to maximize our alpha ij's, right?
We want to
So
maximize our alpha ij's. Yeah.
yes. And what is the logic that tells us that we need to take the minimum between
Because
1 and
look,
this?
so I wish that one of them equals to 1. I agree with that.
Why?
Because
Why there is a solution when one of them is equal to 1 of these alphas?
Because the only thing that you need to keep is this ratio. If you put one of them equals to 1, then another one will be equal to 1 over this guy. Right?
Yes.
Okay.
Okay.
So okay, let us assume. So let us first assume that the right hand side, let me denote it, this right hand side, just by, I don't know, by x, okay? And let us assume that this x is bounded by 1, okay? Then I can take alpha ji equal to 1, to maximal possible, right? And alpha ij, then I will take just to equal to x, okay? This is the solution, right?
Yes.
I cannot make it larger because I should to preserve the ratio of alpha ji over alpha ij, and alpha should be bounded by 1. So this is a maximal solution. In the opposite situation, if x is more than 1, then I cannot put alpha ij to be equal to x, because x is more than 1, right? But then I will put alpha ij to be equal to 1, equals to 1, and then alpha ji, it should be equal to what? To x to the power minus 1. You see, this is again maximal solution.
Yes, okay.
This is exactly what is written down here. Because how do you obtain x from x to the power minus 1? You should just what to say, rotate, перевернуть this guy, right? Okay, so this is a maximal solution. Let me then make another 2 remarks, which will be useful, which will be very useful next. So this is a remark 31. Actually, we need to know pi only up to a multiplicative constant. multiplicative constant. Look, because here you use only ratio of pi I over pi j, right? You do not need to so if you know not pi, if you know only some constant times pi, then it's sufficient for you. For the moment, it looks strange because I mean, it would be natural to assume that you know your stationary state just exactly, not up to a multiplicative constant, because moreover, if you know your stationary state up to a multiplicative constant, you can easily compute this constant. How? Just the sum of components of pi should be equal to 1, right? So sum of components of pi should be equal to 1, and in such a way, if you know, if this vector is called pi hat, then just constant equals to the sum of components of the vector pi hat to the power -1, right? But the problem in applications, and you will see this, that this is sometimes you know this guy, but this guy pi hat, but it is this computation is very complicated. If the number of elements, if the length of the vector pi is large, then this computation sometimes is very complicated. That's why this remark is crucial. Okay, so you will see this on the example I will discuss later. And remark 32, if the transition probability matrix for the initial Markov chain was mixing, then the new transition probability matrix which consists of the transition probabilities Q is mixing as well. You see, because I hope that you remember that the mixing property of the transition probability matrix, this is a property of the graph, right? So you need to know which transitions probabilities between which states are non-zero, right? But when you modify the Markov chain according to suggested algorithm, if the transition probability between two states was non-zero, then it remains non-zero, right? For these probabilities, transition probabilities, this is clear, and for this is also clear because alpha ij is bounded by 1. And also we get that alpha ij in particular they are positive from this construction. Okay, so now time is it? Oh, okay.
Sorry, in the previous remark, what was our claim? We cannot calculate this constant C? What?
Oh, the claim was that. So we need to find this new Markov chain for which the stationary state, for which pi is a stationary state. We do not need to know pi exactly. We need to know it only up to a multiplicative constant. That's a claim. Because to compute this alpha ij, I need to know only the ratio of pi I over pi j. You see?
Exactly. Okay.
Voila. And then I just explained why this is. I tried to explain why this is important. And the explanation is that sometimes in applications, you know only pi up to a multiplicative constant. And then when you are trying to compute this constant, it's easy to do, right? Normally it's easy to do just from this relation. But when you are trying to compute this, you find this computationally, this is a very hard problem because this sum is very, very large. You see? So that's why this remark is important.
Okay.
You'll see it on the application. I will discuss next. So, okay, this was a Metropolis Hastings think how to construct a Markov chain such that a given distribution is the stationary state of this Markov chain. So this was some abstract simple observation. And now let us pass to the next part, which is okay, I will say Markov. In general, this type of methods is called Markov chain Monte Carlo method. So this is a large, family of methods, Markov chain Monte Carlo. But now I will talk only about decoding texts. So what is our problem? Look, we have a text. Voila, for example, which looks like this. What is this? This is, we assume, so, and we wish to understand what is written down here. We assume that this text is encoded. And we assume that this is encoded in a simplest possible way, just one by one. It means that you have a bijection between the Latin alphabet. So if this text were in Latin, were written with Latin alphabet, and we have a bijection from the Latin alphabet to some set of special signs, right? For example, you write the letter A by this, you write the letter B by this, letter C by this, etc. Okay. Equivalent problem clearly is the following. Oh, well, more or less equivalent. Let us assume that the alphabet by which you encode your text is also just Latin alphabet. In other words, yes, and then the encoded text will look somehow like this. And this is an example where in such a way the text of Hamlet was encoded. This is more or less the phrase which you are given, and you need to recognize in this phrase this one: enter Hamlet, ham to be or not to be, blah blah blah. Okay. Well. So how to do that? Let me write down again what we are given. We are given some phrase S. In the example above, it was what it was: enter Hamlet, ham to be, etc. Enter Hamlet. So this is some phrase which is a phrase in, for example, in English language, which has some meaning. Okay, and we know, but we want to find this phrase. We need to find it, but we are given a permutation of this phrase. Here, sigma star is a permutation on Latin alphabet. And we know the action of this permutation to the phrase. So if S was S0, S1, S2, etc. S certain M. Then here we know sigma star of S0, sigma star of, so we had the following vector. Now we have the vector sigma star of S0, sigma star of S1, sigma star of S2, etc. sigma star of SM. Sorry, just a second. And in our example, this phrase sigma star, it looks like that, right? Sigma star of S. In order to find this phrase S, we need actually, it suffices to find the permutation sigma star. This is a decoding permutation, right? So how we could do this? The idea is as follows. Let us look at the text as at a Markov chain, and let us compute the transition probabilities of between. Yeah, then what we are doing? Then we take some well-written text in English language. If I assume that the encoded text is in English language, then let us take some well-written text in English, for example, Hamlet, or I don't know what you wish, and then according to this text, which is written in good English, you compute statistically transition probabilities. So consider a text as a Markov chain and find statistically transition probabilities. Let me call them Rij, where Ij, these are elements of Latin alphabet. This is Latin alphabet. According to any text which is written in good English. Okay, then we will call the probability of a word the following thing. If you have word I1, I2, I3, etc., In, this is the initial probability of I1. Now I write just the definition of Markov chain, the equivalent definition of the Markov chain, which gives the probability of such trajectory. Then R I1, I2, R I3, I4, etc. R In minus 1, In. Okay. Now look. Now actually, okay. This will be later. Now I can compute the probability of my decoded word of this sigma star of S. This is P sigma star of S0, 0 R sigma star of S0, sigma star of S1, etc. R sigma star of Sn minus 1, sigma star of Sn. Okay, right? How do you think will this probability large or not if I take just arbitrary sigma star? How do you think, actually? Look, so how did we define the probability? We defined it according to well-written text in English. For example, in well-written texts in English, words which have okay, maybe let us think about Russian. It will be slightly simpler. If in Russian you have, so it is quite rarely that in Russian you have combinations like that, и краткое я, right? So because just there is no words with such combinations. That's why the transition probabilities which you will find statistically from и краткое to я, this will be more or less 0, right? But and so on. The couple of letters which you can frequently find in text, the transition probabilities between them will be large, but transition probabilities between such couples they will be small. But then if you take arbitrary encoding of your alphabet, for example, it may happen that the letter R sigma star of R is и краткое, sigma star of O is я, and then in this text, in this encoded text, it's quite okay that you will find these two letters и краткое я, because it just means that in the real text you had RO, but RO, this is a couple of letters. This is a sequence of letters which is frequent, right? So, but I measure this probability according to the transition probabilities which I computed according to well-written text, which is not encoded, right? That's why if you just take arbitrary sigma star, it's natural to expect that this probability will be small. Will be quite small. We're rather small. Is this idea clear?
Yes.
There is a question in the chat. Okay. But for which okay, very good. But then I'm going to do the following thing. Let me denote by S star this sigma star of S, and then I will compute for different transition for different transpositions. Sorry, not for transpositions, for different permutations, the probability sigma of S star. How do you think for which permutation sigma this probability will be high?
Permutation that decodes the cipher text.
Exactly. Okay, this probability is expected to be high for sigma equals to sigma star to the power -1. You see, because then you'll obtain a real phrase in good English. Okay. Well, then what I'm doing, I consider the permutations sigma. I choose the permutation sigma at random. Choose sigma randomly according to the distribution according to the distribution pi of sigma, probability of sigma equals to probability of sigma of S star. So next I wish to choose, let us assume that I can choose just sigma randomly, independently, according to this distribution. Not sigma, choose sequence of sigmas. Sigma 0, sigma 1, sigma 2, etc. randomly, then identically distributed according to this distribution. Then look, then with high probability.
What is the distribution we use to generate the sigmas? I do not understand.
This is the following distribution. The probability of given permutation sigma is the following. The probability which is computed according to this rule, compute this probability on the phrase sigma of S star, and S star, this is a phrase which we are given. Okay, so we expect that this probability will have maximum for sigma which are equal to sigma star, or at least which is close to sigma star. So so you get maximal probability. With highest probability, you will get the permutation which decodes, or which is like almost decodes your text.
But to generate this probability, to calculate this probability p sigma, we need to like brute force all the sigmas.
Very good, very good, Camille. Very good, Camille.
But there is too many of them.
I will say about this in a moment. I will say about this in a moment. But this is a very good remark. Look, so this is what I would like to do. This is what I would like to do. And then with high, if I manage to do this, then with high probability in a certain time, I will find. So I will get the decoding permutation sigma star to the power -1, which I actually need to find, right? But as Camille has just remarked, we have a great problem. How to realize this? How to realize this? In order to realize this, we need to compute these probabilities. But in order to compute these probabilities, what you need to do? You need to just, by brute force, you need to consider all possible permutations, and for all possible permutations, you need to find this probability, right? But how many permutations do we have? Since we have 27 letters, then we need to make this computation 27 factorial times. But this is equivalent. This is equivalent, even more complicated than just to subsequently consider all the permutations and try to decode my text by this permutation. So this doesn't make sense, this solution, right? So we arrived to the initial problem which we had. Yeah, initial problem, I didn't mention it, but the problem is that it is impossible to do to solve this problem by brute force, because the brute force solution, what is this? This is just you consider one by one every permutation, and you apply this permutation to this encoded text, and you are trying to find sigma star to the power -1 in such a way, right? But the problem is that you have 27 factorial cases to consider, and then when we are trying to to follow the strategy I suggested, this probabilistic strategy, we arrive at the same problem. We have 27 factorial cases to consider. So that's why we need to modify this strategy. The modification is as follows. Instead of considering this sequence of independent, identically distributed random variables, we will consider a Markov chain, the construction of which will be much simpler. So instead, we will consider a Markov chain sigma 0, sigma 1, sigma 2, not consider, but we will construct. We will construct sigma 2, sigma 3, etc. Such that this distribution pi of sigma star of S, just let me think a second. Just let me think a second. Just a second. Yeah. For which sorry. Such that this distribution sigma of a star okay, let me write it more accurately. Such that pi equal to pi sigma. So sigma belongs to all permutation of the Latin alphabet, and pi, each component pi sigma equals to the probability we are interested in, namely equals to this probability sigma of a star is stationary. And also, I wish this Markov chain to be ergodic. But what we will then have? If this Markov chain is constructed, then we know that the distribution of this Markov chain will converge to the unique stationary measure, and this convergence to this stationary measure, and this convergence is exponential, right? It means that if you then consider your sequence, the probability that sigma, like starting from some m, which is very large, m plus 1 sigma is different from sigma star to the power minus 1, sigma m plus 2 is different from sigma star to the power minus 1, etc. Sigma m plus k is different from the sigma star to the power minus 1. For large k, this probability is small. Look, because the probability, because Pm, it is for large m, it is already close to the stationary state pi, right? And for the stationary state, this is exactly the distribution we wish to model, right? This is distribution we wish to model in this our idea when I suggested to consider independent, identically distributed random variables exactly with this distribution. But here the problem was just we do not know a method how to construct such a sequence. because we do not know a method how to find this distribution, a method which would be computationally efficient. And here I suggest to find, in fact, I just find a sequence of random variables which starting from large numbers, starting from some m, which almost have the desired distribution, right? And then with high probability, I will get for one of these guys with m sufficiently large, one of sigma L is sufficiently large, with high probability will be just equal to this sigma star to the power -1. Okay, is it clear? I feel that I'm explaining not very properly today. I don't know why, but well, is this clear?
How the claim about the probability distribution implies the equality of permutations, but maybe not equality, but somewhat closeness.
I didn't understand the question.
We just claimed that probability distributions, this
Okay.
P power m tends to converge to our stationary distribution. How does this convergence imply that our permutations are close to each other?
Look, then I take realization of my Markov chain, right? So just I start from some state, and I get a sequence of random variables, and I take a realization of the sequence, right? Then the probability, if you take sigma L with large L, its distribution of this sigma L is close to pi, right? Its distribution,
exactly, yes,
pi L, it is close to pi, right? What does it mean? It means that with high probability, this sigma L, as we have already discussed, it is close to sigma star to the power -1 with high probability, and the probability that it doesn't equal to this is small. It means that if you so this is like a coin. This is like a coin where the probability of head is high and probability of tail is small. And then you start to throw this coin. When you throw this coin once, it's okay if you have a tail. But if you throw this coin 10 times, it's the probability that you will not get heads is very small, right? And that's what's happening here, because not only PL has distribution which almost equal to P, but PL plus 1 is also has distribution which is very close to pi, and pi L plus 2 also. So this like your random variable sigma L with high probability it equals to sigma star to the power -1. Your random variable sigma L plus 1.
Sorry, sigma star to the power of -1 is a deterministic object. It's not a random variable.
Yes. So sigma star to the power -1. This is decoding permutation. You see? So as we have discussed,
Yes.
this probability, it becomes maximal on this. So, well, we expect that it becomes maximal on this sigma star to the power -1. You see? And that's why, in such a way, like you construct a sequence of random variables such that each random variable with very high with high probability it equals to the sigma star to the power -1, and then you obtain a sequence of such random variables, and then of course you expect that earlier or later one of these random variables will be equal to the sigma star to the power -1, or at least it will be close to it. Okay.
Okay.
So, well, and so this isn't actually clear at all that this method really works. I mean, because there are a lot of assumptions. For example, the assumption that we expect that this probability is maximized is maximal for this permutation sigma star to the power -1, etc. But in fact, it works. For example, let me show you the realization of this algorithm. When you decode this phrase, and you start your encoded phrase is like that. You see this line. So then after. In fact, this is not the encoded phrase. This is the phrase after 100 of steps of the algorithm. So one step, it means that you compute so you had PL and you compute so you had sigma L and you find sigma L plus 1. Okay. After 100 steps, you have this phrase which does not have any meaning, right? After 1000 steps of the algorithm, it isn't really better. But after 1600, it's already not so bad, you see. It's Estel, well, it isn't clear what is L, but you have almost Hamlet. It is not yet Hamlet, it's Hamlet. But then after 2000 steps, you get the phrase you are looking for. So this is very nice, I think. You see? Just 2000 steps, which is not at all, which is not so large. Only 2000 steps of the algorithm, and then you get the phrase which you are looking for. And you see you are stabilized actually on this phrase after 1800 after 1900 times iterations you already have this phrase, and then you're just stabilized. Okay. So the story of this so I learned this algorithm from this paper by Percy Diakonis, who is a specialist on things like that. And the story was as follows, actually. Military some military guys in USA, they found that in a prison, people who were in prison, they sent letters. They had some correspondence between them using some encoded alphabet, and they just found a letter which was written in such a way, and then they wished to decode this, and they asked Percy Diakonis to do that. And then he gave this as a coursework to his third-year student. And then the student he trained on this problem with Hamlet. He computed the transition probabilities as far as I remember, also using the text of Shakespeare, maybe even on Hamlet. And then after that he tried to decode this text, and he managed to do that. The result is here. What is nice is that here you have some slang. Also here you have some words written in not in English but in Spanish, I think. But in Spanish, yeah, you see respeto. It isn't English. But it's close, and the algorithm recognizes this. Of course, they have obtained not exactly this text. They obtained almost this text, and they worked in order to finish decoding by hands. But the algorithm managed to do this. You see, this is quite nice because here you find the phrases like por favor, like this, which you cannot find in the text of Shakespeare. But it works. It works. Okay, so just
sorry, can I ask one more question? So in this modification, how did we eliminate the problem with brute forcing through all the permutations, because just to calculate, for example, our stationary measure, we still need to iterate through all the permutations.
No, because we do not need to calculate the stationary measure, because I need to calculate only this PL, PL plus 1, and so on. And they become close to stationary measure. Actually, I do not need to create the measure. I need only to have this sequence.
Okay, right. We do not need a measure. We need to.
I'm sorry that I'm in the lecture is very long today, but let me just finish this. What I'm going to explain next. This is exactly what you're asking about. Just how to implement this. The implementation actually is by using this Metropolis-Hastings algorithm, which I suggested in the middle of the lecture. This one, because here we have exactly what we do exactly what we need. So we have a measure which we need to be stationary, and we construct a Markov chain such that this measure is stationary for this Markov chain, right? So this is exactly what I wish to do in my problem, because I have a measure. I have a measure. Where is it written? Yeah, here is it. This measure pi, and I wish to construct a Markov chain such that this measure is stationary. In Metropolis-Hastings algorithm, I started from some different Markov chain, right? And then I modified it in such a way that the given measure is stationary. Here I will do the same thing, so I need to start with some Markov chain. Which Markov chain I will choose? I will choose the following Markov chain. Okay, how to implement it? I will choose the Markov chain as follows. So this will be the Markov chain. Yeah, so let us assume that we have a state sigma m, so that we have already constructed the first m random variables. Then I do the following. Sorry. Yeah, no, sorry. I will explain it in different way. This will be simpler. So first I consider the Markov chain. The Markov chain sigma 0 hat, sigma 1 hat, sigma 2 hat, etc., which is given by the following transition probabilities. So probability to go from sigma to permutation sigma to the permutation sigma prime is given by 1 over n. I will write down what is n in a second. If sigma prime equals to sigma composition with t for some permutation t, for some not permutation, for some transposition t. For some transposition t, and it is given by 0 otherwise. So look, if the two permutations, yeah, and n this is number of transpositions. So actually, what is the number of transpositions? What is the number of transpositions? Transposition, do you understand what is a transposition, right? So
sorry, this n, big n, it is the same n as in 1 over n, right? But there we have like sigma prime equals sigma composition with one transposition.
Ну, это легально вообще так делать?
I didn't catch.
Why do we talk about number of transpositions when we apply only one transposition to sigma to obtain
No,
sigma prime?
T is not fixed. T is not fixed. Let me
It is only one transposition, right?
let me write it more accurately. So it equals to 1 over n if there is a transposition T such that
Oh, okay.
sigma prime equals to sigma composed with T. Okay. Now it's okay. Yeah.
Yes.
So
yes.
n is number of compositions. How many transpositions do we have?
It
How many
is
transpositions do we have?
polynomial coefficient. N
So
multiplied
this is-
by n minus 1 divided by 2, right?
This is number of, so we have 27 letters, so that's why this is the number of transpositions, right? Okay, I consider such a Markov chain. Very simple. So I go with equal probability, I make random transposition in my transition probability. And then I will modify this Markov chain in such a way that my distribution pi, which I wish to be stationary, becomes a stationary measure. So let us modify the transition probabilities Pij via Metropolis Hastings algorithm in such a way that that pi, I recall that equals to pi sigma, and pi sigma this equals to the probability which we compute according to, as I explained before, of sigma of a star is a stationary state of a new Markov chain. So according to Metropolis Hastings algorithm, which we already discussed, the new Markov chain will have the following transition probabilities. So I should multiply 1 over n by alpha, right? So I will get alpha sigma prime over n if there is a transposition T such that sigma equals to sigma prime composition with T and zero otherwise, and alpha sigma prime, it equals to what? According to the Metropolis Hastings algorithm, it equals to, let us look at that formula. That formula equals to minimum between 1 and Pj times Pji, pi j times pi ji. Okay, so this is minimum between 1 and pi sigma prime over pi sigma, because p sigma prime equals to p sigma prime sigma, and they are cancelled in this ratio. So what is the sorry, and here it shouldn't be here it should be 0 if sigma prime is different from sigma, and here also I should write that sigma prime is different from sigma. Here I should write that sigma prime is different from sigma. So if I write that sigma 1 is different from sigma, then I should subtract Oh, no, it's okay, sorry. Yeah. So I do not consider the identical transposition, right? Then here I should also add 1 minus sum of alpha sigma prime over n over all sigma prime is different from sigma, like that. I write badly today, I'm sorry. Don't know why. Well, and alpha equals to that. Let us try to understand the interpretation of this story. What I'm doing. So, and this is a new Markov chain. And for this Markov chain, pi is the unique stationary state, as we wished. So actually what we are doing, this Markov chain does the following. First, I choose at random, so I start with some permutation sigma 0. Then I choose randomly transposition with equal probability, right? And then if stationary probability of this new permutation obtained by the transposition applied to the old permutation. So maybe I'll write like this. If this new permutation obtained via applying the transposition to the old permutation, if its stationary probability is larger than the stationary probability of the permutation you are situating at, then this minimum equals to 1, and then it means that you go to this new permutation, right? So here you realize this passage. But if not, if the stationary probability of this new permutation is smaller than the stationary probability of the previous permutation, then you will do this permutation, but with some probability which is less than 1. You see? And that's what you are doing. And in such a way, you obtain the sequence of these random variables, etc. And then you expect that the distribution of your permutation number n, for n sufficiently large, it is close to the stationary measure, which you need, because this according to the exercise not to the exercise, to the remark, which was this remark? Yeah, to the remark 32. If the initial Markov chain was ergodic, then the obtained Markov chain is ergodic as well. Oh. According to sorry, to remark 32, Markov chain with transition probabilities Q sigma prime is ergodic. Since the Markov chain with transition probabilities P sigma prime is ergodic. And this is the exercise. This is the exercise. The last thing which I would like to note, I apologize again that it's very long, but the last thing which I would like to note is that here we need to know only only pi sigma prime over pi sigma. So we do not need, we need to know pi only up to a multiplicative constant. Multiplicative constant. You see, and this is remark 31. This is remark 31. Why here it is important? Here it is important because when you are trying to find, so look, actually, in order to construct this Markov chain, you could say that we again need to know all this pi sigma, and we need to perform the same computation from which we started. So our problem was that we cannot just find this computation because this stationary state pi, because the computation is too complicated, because the number of permutations is 27 factorial is too large. But no, here we do not need to know all pi sigma for every sigma. Let me even write it. We do not need to know pi sigma for every sigma. Otherwise, we would have to make to find 27 factorial terms. We do not need to know them, because we need to know only those sigma and sigma prime through which we pass. But their number is much less, because the conversion to the stationary state is quite fast, and this n for which the distribution is already close to pi, this is not too large. You saw on the example that is like 2000. So we need to compute, instead of 27 factorial objects, we need to compute only 2000 objects. You see, another problem would be if we would have to know this constant, which equals to the sum over all sigma pi sigma. Because in this case, we would have to compute all these pi sigmas, which are 27 factorial. But no, we do not need to know this, because we need only this ratio. You see? Okay. This is the time to stop. So do you have any questions?
So we theoretically imagine some Markov chain, but in the reality, we just take a initial state where we start with permutation. For example, we take a permutation, some permutation, and then we check like 2000 of transpositions to see what are the images of this of our permutation under these transpositions. So like we need to calculate distribution for sigma 1, right? And this conclude
No. Look, Camille,
we cannot work with the Markov chain as a whole, because there are 27 factorial in transition probability matrix.
Yes. So the Markov chain, so this story with the Markov chain, with the stationary state and with Metropolis Hastings algorithm, this is the explanation why this works, why this algorithm works. But in reality, what are you doing? In reality, you are doing the following thing. You start with arbitrary permutation. You check, okay, it didn't decode the text. Well, let us go further. Then you choose at random transposition T. Okay. random transposition T. Then you consider psi sigma prime 1, let me call it, which equals to sigma 0 composition with the permutation with the transposition T. Okay, you consider such permutation. Okay, then you compute this ratio, this one, pi sigma prime 1 over pi sigma 0. If it is larger than 1, then you just, it means that here you do not modify your Markov chain, which is this one, where you make random permutations. It means that you take sigma 1 equal to sigma 1 prime. Okay, but if this guy is less than 1, more than 11, is less than 1, then you should modify this Markov chain. Then you have here, you multiply by this factor alpha. Then with probability, this p sigma 1 over p sigma 0, you take this permutation, you take sigma 1 equal to sigma 1 prime, but with probability, with the remaining probability, 1 minus this probability, you take sigma 1 just the same, sigma 0, yeah, sigma 0. This is this situation. Ah, wow. Here, sorry. Here I should have written that this case, this is sigma equals to sigma prime. So with this probability, sigma equals to sigma prime. You are in this case. Okay? This is the algorithm. What are you doing? This is the algorithm. What are you doing? So at each step of algorithm, you need to compute only one ratio. Only this thing, this first, and second, you need to choose random permutation. And that's it. And the claim is that the distribution of sigma n converges to the stationary measure pi. Okay?
Okay, but we need a permutation, not a distribution.
Yes. But then you continue to construct this. Then you construct sigma 2 in the same way from sigma 1, right? So you constructed sigma 0, then sigma 1. Then
Yes, but for sufficiently large n, we have sigma n. What can we say about sigma n?
We can say that its distribution is close to the stationary distribution. But this means that with high probability, sigma n is close to this decoding permutation. With high probability.
Oh. This is due to the fact that the decoding permutation is
maximize the
mode of, yes, okay, so I understand, right?
Yes, so this is, you see, this algorithm, what is the explanation, what is the empirical explanation of this algorithm? Look, I do the following. I start with some permutations, and I change it randomly. How do I change it? But just by simplest possible way, I make random permutation. Then I look if the stationary, if my new permutation, this sigma 1 prime, is better than the old one or not. What does it mean that it is better? It means that it is closer to sigma star to the power minus 1. What does it mean that it is closer? It means, we expect that it means that its stationary probability is larger than the stationary probability of the previous permutation. Okay, if it is larger, then very good. We take this new permutation, you see? So yes. For sigma 1, we take this new permutation. But if it is worse, it would be natural just not to take it, right? But no, it doesn't work. We should take it, but with some probability, which is very small if this new permutation is bad, because if this new permutation is bad, is much worse than the previous permutation, then this ratio will be small. Then we will take it, but with small probability. Why we should do this? This is like when you have a function, and you wish to find a global maximum of this function. Look, the problem can be that you approach to local maximum, and so what are you doing? You take your point and you choose some point, and you choose at random points which are close to your point, and you compare the values of the function, right? Let me.
Yes, this is exact replication of this problem. We're searching for maximum of probability distribution.
Yes, exactly. So the problem is that if you are here and you choose a random point which is close to your point, if you are at local maxima, then choosing any close point to your local maxima, you will get that the value of the function is smaller than here. But this doesn't mean that this is a global maxima. So it means that if you, via such a random algorithm, are looking for a global maxima, it means that with some small probability, you should choose the points which are worse than your point. Because if you are here with some small probability, you will choose, say, this point, and then it will be able to, you will be able to arrive to a global maxima.
But we can still,
they work in such a way.
it seems that we can still end up in a local maximum in our algorithm, don't we?
Yes, we can, but then we should check what is the result, if the text is indeed decoded or not. Yeah, that's what I said, that you may have quasi-stationary states. That's what I meant in the beginning. In the beginning, I told that the problem is that you may have quasi-stationary states. Yeah, I mentioned this maybe when I was talking about the page rank, because you may have the same problem. So your sequence is like stabilized. Your sequence of distributions is stabilized for a long time, and then you think that you have already arrived to the stationary distribution, but not. You see, this is the same. So you should wait more. Okay, so I think that it's time to stop. Sorry, it was really very long today, but well, I hope that I explained more or less this story. Well, so thank you.
Можно один вопрос про работу, про диплом?
Да.
Не про лекцию. Вот там то, что я вас прошу посмотреть, там в смысле просто...
Сейчас, Камиль, давайте запись остановлю, да, потому что сейчас.
Ага.
Потому что это уже...
Ну, короче,